So today's webinar is all about failure rates, realistic failure rates, and the importance of data integrity. For those of you that do not know me or are new to exida webinars, my name is Loren Stewart. I am a CFSE and I work here at exida. I've been here for about 6 years now. And I work mostly with our mechanical customers, helping them achieve their IEC 61508 certification. But the other half of my job is I teach a lot of our exida Academy courses on functional safety and the functional safety standards. For those of you that are new to the exida webinars, you may not know all about exida and who we are yet. I like to say, no matter where you are, where your customers are, where the products that you're buying are, we have somebody close by for your functional safety needs, whether it's in functional safety, alarm management, or cybersecurity. We have experts close by that can get you the help that you need. exida is involved in the complete supply chain of functional safety. So if you are an OEM that's making products that need to be certified, the whole way through, if you're an end user using those certified products in a safety system, we have consultants, we have tools, we have templates, we have everything to make your life go smoother and easier. exida certification is one of a little bit we're going to talk about today, especially the IEC 61508 certification. That comes along with those failure rates. We're going to especially talk about the data integrity and where failure rates can come from. And one of the routes of getting failure rates is an FMEDA or IEC 61508 certification. But exida does do other certifications as well in not just functional safety, but cybersecurity and personnel as well. And then finally, the last little bit about exida before we really get started is our engineering tools. Again, we're going to talk a little bit about this today in our webinar, and I'm going to actually show you an example with one of our tools. But all of our tools were designed with you in mind to help save you time and money. Well, how does that happen? By increasing your efficiency and helping your productivity. So if you're trying to do PHAs and LOPAs in the beginning of SIF design, we're going to look at the verification portion of it today in the SIL verification. Or if you're the whole way talking about proof tests, alarm rationalization, or cyber, we have tools that can help your job become quicker and easier for you. So what we're going to be covering today, throughout the entire webinar, we're really going to be concentrating on failure rates. We're going to talk what is a failure rate, how you can get them, the different methods of achieving failure rates, and just like everything in life, there's pros and cons to all of these methods. We're going to investigate the two primary methods of estimation and prediction today. Then we're going to talk about failure rates, the different types of failure rates, and look at how having specific failure rates compared to generic failure rates can really adjust your safety calculations by even an entire safety integrity level. And we're going to go through an example of that today as well with that software, one of the modules in the software that we just talked about. Whenever, throughout the entire webinar, if you have any questions, please feel free to write them in the questions module of your GoToMeeting panel. I'm not the best at stopping the webinar or looking up to see if that's blinking at me or not. However, I will take time at the end to stop and answer any questions that you may have. Also, if you're here and listening to this live, you will get an email at the end of this week with a copy of the slides and a link to the recording. It's going to be also posted on YouTube and our exida website if you do want to reference back to it at any time. But let's go ahead and get started today. Throughout the entire webinar, I want to be coming back and always have you think of the importance of data integrity. And that's why I put it so large on this slide. I want you to think of it in the beginning when we bring it up, but then also when we talk about each way of getting failure rates and why it's so important. So when we talk about data integrity, I always say, well, who really cares about failure rates? Well, what are they? Well, if we take a failure rate down to the basics, it is a unit of measure that's showing you the chance of a device doing its job successfully or not, or if a failure could occur. And what do those devices, what are they doing? What are they trying to achieve? Well, those devices that we are calculating failure rates for are what's setting up your safety instrumented functions and your safety instrumented systems. What are those? Those are what kind of is your last line of defense to remove as much risk as needed to get your company down to where they think the tolerable risk should be. So this is after you've already taken into consideration the process, your design, your basic process control systems. This is on top of your alarms and your operator actions. This is on top of any relief valves that you may have. So your SIF is what you put in place when you realize your process is too risky to open up as is. You needed to put an extra set of equipment to bring the risk down to a level that your company is saying that is okay, or the general population thinks is an okay risk level. So when we talk about failure rates, they're tiny, tiny, tiny numbers. They're normally in fits, and that's 10 to the negative 9. That's per billion of hours. That's really, really tiny. And someone might say, well, what's the difference of 10 to the negative 9 to 10 to the negative 8, or 10 to the negative 9 and 10 to the negative 6? They're still very tiny numbers. But when you put it in perspective, it's a tiny number, but that tiny number needs to be realistic. That tiny number needs to be accurate, and it needs to be validated. It needs to be what it actually is and not an over assumption, because that number is assessing how much risk you need to remove from the process before it's safe enough. When we talk about failure rates, reliability engineers seem to know this, but it seems to be taken for granted. Failure data must come from one type of source, and that needs to be quality field failure data operating in similar application. What does that mean? Well, when you're doing your analysis, make sure you're always going to do an apples to apples comparison. If you are a nuclear power plant, do not take the failure rates or the field failure data from a offshore reliability company from the North Sea. That is not going to be the same application. It's not going to be the same operating environment. Once again, high demand and low demand mode of operation. You always want to make sure you're comparing an apples to apples comparison and you're not crossing those. Same with clean and severe service, close on trip, open on trip applications. All of these need to be considered when you're looking at your field failure information or your data sources. You when you are comparing your failure rates, you need to have an as similar application to you as possible. Well, everybody says, well, that's great and all, but says who? Well, now the standard says so. The old version of IEC 61511 just used to say, yeah, use failure rates in your calculations. However, the new version of the standard really upped the language. They made sure that they said not just using failure rates now, but use failure rates that are credible, that are traceable, that are documented, and that are justified. It's not just good enough to use failure rates or any number that you just grab out of the air, put it in your equations, and go. You need to have it to be based on field feedback from similar devices used in a similar operating environment. Once again, this language has been ramped up from the previous version of the standards to make sure that this point was driven home. So now that we know how important failure rates are, what they are, how important they are, because they protect us, they're our last line of defense of removing that risk before an accident could happen. And we know the standard says they need to be credible, they need to be traceable, they need to be documented and justified. So now where do you get these failure rates from? Where can you get this information? You want to use good information. How do you get it? Well, there are two main ways of getting failure rates. The first technique is called an estimation technique. An estimation technique is based on field failure data. We'll look at how estimation takes information, analyzes it, does its statistical analysis, and it can estimate future failure rates given on historical data. The second way of getting failure rate data is from a predictive analysis, and that technique is either based on test results or a design stress strength analysis. And we're going to look at both of these in more detail. So the first one we're going to dive into is the estimation technique, and it's a way that you can estimate failures from looking at field failure reports and using statistical analysis. But you can only do that if you have a good understanding of all of the equipment operation, the component failure modes, key environmental variables, how the equipment is used, and how the data will be used by designers. It's not just good enough to say, we've had 6 of these come back with an issue. That is not enough. Once again, going back to the strong language of the standard, it needs to be credible, traceable, documented, and justified. One of my favorite new quotes is, "Math alone is not enough." And we'll talk about that later on. But if you don't know the pieces of information that you're getting in, no matter how great the statistics are that you're doing to it, it's not going to be worthwhile information. There are 3 main ways of getting estimated failure rates. The 3 most common are industry database, end user field data studies, and manufacturer field data return studies. Just like everything in life, there are pros and cons to each of these 3 estimation techniques. First of all, you have industry databases. This is what they do is one group, one company will gather information from multiple other groups or companies, put that information together and analyze it. This was first started in the 70s or 80s in military databases. There's telecom databases from these techniques. Now more recent are REDA, or the offshore reliability data, and that is a organization that analyzes a lot of the offshore and subsea platforms in the North Sea. They once again take information from multiple different companies, analyze it, and a university runs their statistical analysis, and then they publish a database with that information. The great thing about industry database, this is real information. These are real failures, and depending on how it is documented, this could give you a wealth of knowledge. If you just have a, yes, we had one failure, it's not going to give you so much information. However, if you're doing as found conditions, this could really be very useful. However, make sure you are using apples to apples comparison. If you are a nuclear plant, you might not have the most relative information in the offshore North Sea handbook. Another negative with this is sometimes the pool of devices that is used, that is studied, isn't the largest. And if you have one failure in a small pool will really skew the statistics. So you have to make sure that your data pool is large enough to make statistical sense. The next way of estimating failure rates are end-user field failure data studied. Once again, pros and cons with this is if you have a high-quality data gathering system, this is awesome information. This is site-specific data. This is a gold mine for you end users. Once again, don't just leave it in your data collection system. Actually analyze it. Look at the as found conditions. Look at how the failure happened and trace it back. You can really eliminate a lot of your systematic issues that way. However, a lot of end users don't have that quality data gathering system. They just have maybe an Excel spreadsheet. And think back to what the standard said. They up their language. It needs to be documented, traceable, justified, and credible. Is that giving you that high confidence factor? Another thing is, depending on if you're comparing it to other end users' failure rates, it depends on what people are considering a failure and what they are classifying as an issue and analyzing. We've seen it not just from company to company, but from site to site, sister sites, interpreting, analyzing procedures and documentation differently, thus classifying a failure differently. Another way of estimating failure rates is manufacturer field data studies. Once again, this is great information because it's that real data. This can be for a specific device in a specific manufacturer. However, some bigger issues with the manufacturer field return studies. First of all, you don't know how many you're actually getting back. If you are a low dollar item in the SIF, you might not get notified every time you have a problem. There might be extras just sitting on a shelf, and all of a sudden it's easier to pop out a solenoid and exchange it than to call up you, let you know that there's a problem, and go through the whole warranty repair situation. However, if you're the most expensive part of the SIF, you're probably going to get a call. Once again, not every manufacturer is going to classify a failure as the same way. Same with the end user field failure studies. Some manufacturers will just easily say, nope, this was customer misuse, and write off all of those failures. That this wasn't a problem, this wasn't our fault. Where sometimes that was a little generous to throw all of those in that category. So, with estimation techniques, There are pros and cons with all of these. In addition to all of that, there's always, if you get down to specific manufacturer, make, and model, there's always going to be a limited number of material you're getting in. If you're maybe lumping everything together generically, you might be able to get around that. But by the time you're gathering enough data that it makes statistical sense, you're processing it, analyzing it. If you're especially if you're electronics, things are changing quickly and rapidly. By the time you gather enough data, things might be obsolete. There might be new designs out there. The new designs might not be covered. So there was a recognition that something needed to be better. Something else needed to be done. So reliability engineering came up with the predictive analysis. Just like the estimated analysis, this predictive technique, there's multiple different ways you can do it. This predictive technique is going to predict failure rates based on test results or stress strength analysis. Just like the estimation, there are pros and cons to each of these ways to predict failure rates. The great thing about failure rate prediction is you don't need the historical data. You can predict failure rates for brand new devices. This is great, especially if you are new to the market, if you're electronic. However, might not necessarily be the most important thing if you are a valve. So the first way to predict failure rates is the B10 data point. B10 data is also known as cycle testing that you may have heard of, and that is based on your test results of a repetitive motion. This test, first of all, it assumes that the application has constant dynamic operation. What does that mean? That means you're in a continuous or a high demand mode of operation. So is your SIF a robotic, a machinery application? If so, B10 and cycle testing may be a valid method for you to predict your failure rates. However, if you're in the process industry or you're a SIF that is going to close on trip and you're hoping that you're not seeing a demand on your system once a day or multiple times a day, you're going to be in low demand mode of operation. All of a sudden, B10 is not an applicable option for you. So B10 is only if you are in high or constant motion. You're in dynamic operation if you're in robotics or machinery. The next way to predict failure rates is the MIL Handbook 217. That was brought around in the 70s or 80s, and it was a component database that allowed you to predict total failure rates based on design strength analysis. Then we have the FMEDA, or Failure Mode Effect and Diagnostic Analysis. And an FMEDA is, once again, instead of the test results, it's a predictive technique based on the design stress strength analysis, kind of like the one we just talked about. Once again, it's using a component database that predicts the total failure rates. And actually, the FMEDA process uses a component database that can incorporate the military Handbook 217 in it as well. So you could incorporate both the bottom two prediction techniques. The FMEDA takes into consideration the application, the environment, the service, and it accounts for the failure mode, the diagnostic coverage, and the useful life. So because the FMEDA is more up-to-date than the 217, I'm going to dive into that a little bit further to explain how you get failure rates from that technique. So the FMEDA method was brought about from an FMEA put together with that MIL Handbook 217, put together with diagnostic analysis. And all of that was thrown together to make an FMEDA. The great thing about that FMEDA is it can be done for a newly designed device. So you don't have to know how the device will fail from its history as long as you know the failure rates for all of the components. So what's important when you're doing an FMEDA? That component database. So that component database, it needs to have every component failure rate along with the failure mode distribution. So what does our component database look like? So here at exida, I can't speak for others because I haven't seen those, but our component database, it's broken down into every single thing you need for that device, whether it's a nut, bolt, screw, O-ring, resistor, anything you can think of that's on that bill of material is listed in the component database. And each one of those components has a failure rate associated with it and ways that it can fail. So let's take, for instance, a bolt. A bolt's pretty easy. How can a bolt fail? Well, a bolt can break, it can shear, or a bolt can loosen. So for both shear and loosening, we have what are the chances of it breaking, what are the chances of that bolt shearing. Then when we look at the FMEDA, we look at that bolt in the device itself. So if that bolt does shear, can the device still perform its safety function? Can it still do its job? Or is it going to be prevented? Say, for example, we take a ball valve that needs to close if a pressure gets too high. So if we will look at that bolt in that valve, if that bolt shears, can the valve still close if needed? If that bolt loosens, can the valve still close as needed? At the end of the FMEDA process, you have a product failure rate, an overall product failure rate, your product failure mode, and your diagnostic coverage. When we talk about an FMEDA, your failure rates, they'll not only let you know your dangerous failures, or those failures of that valve not closing, but an FMEDA will also let you know the chances of a safe failure happening, or what are the chances of that valve closing when it did not need to. So an FMEDA is a study of the strength of the design compared to every single stress that we can think of throwing at it. So whether it is from the process itself, from the environment, from the application, we take all of that into consideration and how that device, can it still do its job if needed. In the perfect world, estimation and prediction techniques are going to line up, and they're going to line up beautifully. We would take a device and we would look at its history in the field, looking at its operation hours and its field reports. We can do our calculation to figure out the failure rate, and we want to compare that to the failure rate prediction. That failure rate prediction, if you're doing an FMEDA, taking into consideration the application and the environment. Those two failure rates, they should equal each other. If you're my customers, I always say the predictive method hopefully is going to let you be a little conservative because you don't want to say that you're not as good, or you want to be as good as you're at least saying you are. However, we don't always live in a perfect world, and there are times where the estimation techniques and the predictive techniques do not align. And if that is the case, that's my red flag. That's letting me know that either one or possibly both of the methods are seriously flawed. Take into consideration this example. I have highlighted the second from the bottom, a logic solver, and they're showing that the field failure estimated failure rate to be 1,200, where the predictive technique was 15,000. That's a huge difference. So in this case, I would say, well, I have a feeling both methods might be flawed here. Look at your field failure estimates. Did you get all of your returns? Are you not counting things as failure? Is this a apples to apples operation? Same thing with your predictive analysis. Was this done with the same type of application, or was this a high demand or a low demand when you shouldn't have been? Is this an apples to apples comparison? And then finally, look back at that component database. That's super important with the FMEDA if that's done, because in a perfect world, those would match each other. When we do an FMEDA, we always, every single time, compare estimated results to predictive results. So if there is historical data from a project, we will compare that to the FMEDA results. And always, I call it my sanity check. Make sure we're in the same ballpark. Also, when we perform an FMEDA, we always refer back to SILSafeData.com. That's once again a sanity check. That will have your range of all of these types of devices on failure rates that you can expect to see out in the world. So when we do an FMEDA, our database and our component database is consistently calibrated and validated by always looking at manufacturing data and the field return data. We have end users data coming in. We've done all of the studies with the exida data. We have the military handbook. We have the Siemens data book. We have other databases that were public, all feeding into this component database to continuously update, validate, and check. We started our component database in 1999, and we are continuously updating it, creating new parts if needed, and updating components if needed. So this is all well and good, and that might be great if you have certified products. You will have an FMEDA, and now you know failure rates from that FMEDA. But what if you don't have a certified product, or what if your components don't have FMEDA done? What if you are not in high demand mode, so you can't do cycle testing? Well, what do you do now? What if you still don't have failure rates? Well, this isn't the perfect answer. However, I always tell my customers, I always tell everybody that I teach, use SILSafeData.com. What that is it's a list of types of devices that are commonly found, and it's going to give you a kind of generic title, so a floating ball valve. It's not going to say specifically this product, but it will give you a low bounds and an upper bounds on what to use for failure rates. So this is a great website, even if you have your FMEDA. I always say no matter who gives you failure rates, always check them against this. Make sure you know what you're getting kind of matches that sanity check. Make sure you're never given a red flag. So just to take a look at SILSafeData.com, this is what it looks like when you pull it up. It has those lists of types of devices with a lower bound and an upper bounds rated in fits or failures in time. That's 10 to the negative 9. So let's say, for example, that bottom one there is a triple offset butterfly valve. You can have the different application, close on trip, open on trip, tight shut off, and that gives you a lower bounds and an upper bounds to expect. And it might be a large range because we don't know the complexity of the device that you're actually using. So if you're using this as a generic number, you have to use that upper number as your generic. So what does this look like in a SIL verification? So as I said, I'd show you an example. That's how I learned best. So I wanted to give you one as well. This is what, for those of you that don't know, this is what is our exSILentia. This is our SIL verification module, Silver, and this is what we look. This is what it looks like. I'm going to zoom in on this because I know you can't read this. But I put together a sample SIF, some sensors, logic solvers. I put some final elements, and I'm saying, let's say I don't know what type of transmitter I am going to use yet. So I'm just going to use a generic safety transmitter. I'm going to go to SILSafeData.com. I took the upper bounds, and I'm putting this into my information, and I was able to run the SIL verification calculation. Told you the tools save you time. You don't have to do it. This actually does the Markov models in the background for you, not even the simplified calculations. But this is saying that from our PFD average, our probability of failure on demand, it breaks it into our sensors, our logic solvers, and final element. As you can see here, our sensors is the lowest PFD average, and that's because we're using that generic transmitter in there. So for this example, we have a SIL rating of a SIL 1. But if we took that, all the same information, didn't touch it, but traded it out for a specific transmitter instead, you can see that took care of the sensor's PFD average. And because we know your SIL level is going to be your weakest link, your lowest one, that generic was affecting it enough to drop us an entire SIL level. So I always say don't use generics unless you have to, but it's always an option for you. What if you do have a generic and you are at that SIL 1? Don't panic. There are still things you can do to bring up your safety integrity level, such as proof testing or shortening your mission time. And we have webinars about that as well. However, use specific equipment whenever you can. So I'm going to now take some time for some questions, but we really talked about failure rates, the different ways of getting failure rates, and different types of failure rates there are out there. So at this point, okay, there we just got a question, and I was going to say I have no questions. I'm going to go ahead and read through this question. If you've liked this, hopefully you've liked this. You can come to way more webinars, but if you want a lot more information, we also have training. This, instead of giving you a half-hour or 45-minute look, this gives you a major in-depth look in functional safety. And if you have nothing to do tomorrow, we have a great one presented by two of the heads of our company. So if you can check that out, that would be great. So if you want more information, always look us up. And if you think of questions later, here's my email address to feel free to reach out later. If you're laying in bed thinking about functional safety tonight and think of questions, there you go. Okay, so we have two questions that came in so far. The first, talks about field failure data and how systematic failures are going to be thrown into that. And absolutely. However, those systematic failures are only going to be in there until you've taken care of the problem. Once you go through the phases of the safety life cycle, you know where those systems, because you're a good engineer, you're applying those, you're going back, you're revalidating. Those systematic failures are going to trickle out and take care of themselves eventually. So no matter if you're doing predictive analysis or estimation techniques, you need to count those systematic failures until you've taken care of them and you know you've corrected the problem. The next question is about the SILSafeData.com and the confidence levels of the lower and upper bounds. I believe the confidence level is the 90%. That is what is written in the standard, that it needs to be at least 90% confident in your data quality. So I know it's at least that. I believe on the website it says that, but I'm not 100% positive, so I can look that up and get back to you if you'd like to email me. I can let you know. At that point, we are finished with our questions. If you have any later, please let me know. Thank you so much for joining our webinar, and have a great day.